Good. So thanks a lot for the invitation, and I'll try in this first course to explain what are the motivations. In short, the title, as the title suggests, it is new, but it's really rooted in a classical theory. I chose De Giorgi because most of the time I follow an approach of De Giorgi, but it's a classical theory by several super famous mathematicians. De Giorgi, Nash, and Moser are the most famous ones. Sometimes I will refer to the series of papers they produced, the Guerand-M theory. And to be fair, at about the same time, a paper I like a lot that I think should be added here. Well, actually two papers by Kruskov are absolutely beautiful, exactly at the same time on the same topic. So in short, what I will try to convince you in this course is that there is an extension that is non-trivial, useful, and beautiful, usually the three qualities that we like as mathematicians, of this classical theory to the class of equations we encounter in kinetic theory. So I start in the title, I chose in the title to use kinetic theory because I like things to be motivated by mathematical physics. But if you want to think in terms of class of equations, what I'm really interested in is the extension of this classical theory to type 2 hypoelliptic PDEs. In the sense of Hermander, I will explain that now. And an additional feature that we encounter a lot in kinetic theory is non-local operators. Okay, so that is the very short summary. I would like to understand how we can extend this classical theory to type 2 hypoelliptic equations occurring naturally in kinetic theory, and if possible, non-local. I don't know if I will have time to arrive at non-local operators in this course, but that is the idea. So the plan, the tentative plan is the following. I'll introduce the motivations. Three main motivations: the 19th problem of Hilbert, the Hermander theory of hypoellipticity, and the problems of mathematical physics in kinetic theory. So I'll explain these three things in the introduction. Then I'll spend some time to do the Giorgi, let's call it the classical theory, because if I immediately start explaining the extension, I would have to redo a lot of these arguments anyway. On this, I will follow for at least an hour and a half, or an hour, maybe an hour. I will follow some very nice lecture notes of Anceschi-Rebucci in a series of lectures he gave to Beijing University about 10 years ago. And then I will go on discussing the extension to kinetic theory. So it turns out this theory is usually split between two lemmas. You will see what we call lemma 1, lemma 2. So the first lemma of De Giorgi in kinetic theory, and then the second one. The first one really deals with the gain of integrability. The second one with a gain of Hölder regularity. So the first one is an improvement of integrability. The second one is a reduction of oscillation under scaling. And then I will discuss Harnack inequality. In particular, extending Harnack inequality to the kinetic setting and making it quantitative was very interesting. And for me, I will try to explain. I think it allows to understand also better the role played by the log in the various approaches of De Giorgi, Moser, and Nash, and Kruskov. And the rest, I hope I will have time to do it, because I have a few more hours than the first time I gave this course, is the connection to trajectory, so trajectory control theory and hypocoercivity. It's not really mysterious why trajectories should be studied. That I will be able to explain in this, this class. Because for those of you who know already, Hermander theory is a theory about commutators between vector fields. And one way to understand how they commute is to build trajectories using all of them to connect any 2 points. So you can reframe the commutator condition of Hermander as a problem of constructing certain trajectories. And that, I don't know if I'll have time to do this, the issue of non-local equations. By non-local, I mean think to fractional Laplacians, for instance. I'll see what I have time to do. Okay, so let's start with the introduction. And so this is a sort of new theory, but it's old at the same time. So let's start with where it comes from. If you want to give it a name, it's the regularity theory of certain class of PDEs, let's call them just kinetic equations, with RAF coefficients. RAF usually means merely measurable. It's extremely natural in PD analysis because it corresponds to, as I will explain, to dealing with nonlinearity. It's also natural in some part of stochastic analysis, and it is interesting in itself as well. It's really about understanding the structure. So, the first origin is in the 19th problem of Hilbert. So it comes out of the mathematics of the 19th century, which studied a lot the calculus of variation. So one of his famous problems at the ICM in 1900 was about whether, so I'm trying to get his formulation. Yeah, he wanted to know which are the regular variational problems. So that is the question. And by regular, for Hilbert, a regular variational problem means in this context, means that in practice, formulated in modern terms, the Euler-Lagrange equation for the minimizers have analytic solutions. Okay, so those of you doing PD analysis, you might say, well, immediately I have a bad reaction to analytic. It's not really the problem here. It was understood very quickly that C infinity would imply analytic. And quickly afterwards, that C infinity itself is not really the problem. A certain amount of Hölder regularity implies C infinity. The problem is at the start, not at the end of the regularity ladder. Okay, but that was the question of Hilbert. Of course, you can't do that for any Lagrangian, so we'll have to put a certain amount of assumptions on the Lagrangian. But, and the question proving analyticity is because, well, at that time, it's the highest order of regularity, and it was used a lot, I guess, in the 19th century. So let's start writing things a bit. So this is about the smoothness of the local minimizers. Local because, well, I will actually only look at the extremum condition solving, which is about solving the Euler-Lagrange condition. So let's consider U bounded open domain in Rn, and let's consider L a Lagrangian, which I will, sorry, L goes from RD to R, and we'll have to assume something in a second, typically some sort of growth, some sort of maybe coercivity, convexity. I'll come back to that. Maybe there will be boundary conditions. You'll see in a second why I don't want to talk about boundary conditions. We'll forget them completely for the rest of the 8 hours because I will only look at interior regularity. So I won't discuss anything with the boundary. And now the variational problem is about minimizing something of that type. So you define a certain functional E for energy, and you integrate your Lagrangian taken on nabla U, and you want to minimize that where U belongs to something, a certain function space. Of course, you want a function space to at least make sense of that, and potentially with boundary conditions. Examples. So I'm starting with the very classical motivation for Hilbert problem. Examples, if you take the harmonic energy, the basic harmonic potential, so the standard energy, you get what you get is simply that E is the Dirichlet energy. And the other standard example is if you take L of P to be root 1 plus P square. This is actually just, so I mean the standard interpretation. If your is your height function that determines the surface, this is just the element of area on the surface, and therefore E is just an area, right? E is just measuring the area of your surface, and you have the minimal surface problem. Okay, these are the super standard examples. And therefore, in the case 1, you write down the Euler-Lagrange equation, and you obtain, obviously, the standard Laplace equation. And of course, I don't tell you what I do on the boundary for now. And in the case 2, you write down the Euler-Lagrange equation, and you get, well, sometimes people prefer to put it as with a minus to have a positive operator, and you get minus divergence of grad U over that 1 over the surface element, the area element, again with certain boundary conditions. Okay, so this one is the real motivation. That was well known. Of course, if you solve that, you're harmonic, right? You're locally your own average, so you have regularity. This was, of course, known. That is less clear already. And usually, courses taught on advanced elliptic equation, they heavily use that example to illustrate the Giorgi theory, the Giorgi and Hölder. Okay, because this is non-trivial. You can see that there is a non-linearity. And if you just try very naive energy estimates, it won't just work. You'll have to do something better than that. So in general, let's look at the Euler-Lagrange equation slightly more generally to explain how the Hilbert 19th problem was solved, and that will help us to arrive at the formulation for kinetic equations. In general, if we derive the Euler-Lagrange equation associated to my variational problem, at that point it's formal. I don't have any function space or anything. You would just get, of course, you you just expand with an increment that is making sure you stay in your function space and everything. So you write down having a minimization problem, and formally you end up with the equation, well, let me write it one last time. You end up with, put one too many, sorry, like that, yes, no, like that. So that's your first order term in epsilon. You have to cancel that, and that is a weak form. Okay, weak because I integrate by part ones away from the boundary, and that is the weak form of divergence of L grad U is equal to, of grad L grad U equal to 0. Let's write it once more in a slightly more explicit form. In fact, if I expand, it means, chain rule, that I have the second derivative of L at the gradient. Now this whole thing is a matrix, and I contract it with the second derivative of U. Okay, so that is my Euler-Lagrange equation in general, and that is a non-divergence equation. Okay, so there's one thing we can do. I'll record. There's another manipulation to do. It's slightly out of order, but let me write it here so that we have both things on the blackboard, and then I'll discuss the history of how the problem was solved. It turns out that if you define, so one more observation, if you define f to be one partial derivative of U, okay, so it's formal at that point. I assume U to be regular. Then the equation 2 stars implies on this new unknown f. So it's better seen here. You just dxk that form, and you get that f will satisfy divergence of the same matrix here applied to grad f. And that is a divergence form PDE on the first derivative of U. Okay, so let's call that matrix A. And we have two nice problems, two nice elliptic problems on U and on the first derivatives of U. So an additional remark, like I said, here I will only deal with interior regularity in these lectures. So we no need to specify, to discuss the boundary. Doesn't mean it's not an interesting problem. Just that I won't discuss it. Just as a remark, in kinetic theory, this has just started like 10-15 years ago, so there's still a lot to do. And in particular, the regularity properties at the boundary have been barely touched. There's a few results by UJ, by Francesca Anceschi, but there's very little at the moment. So a lot remains to be done here. Okay, so now let's make some hypothesis on K, on L, sorry. So typically, we want to assume the following. L is a smooth function that is reasonable in physics, okay? The second one is a little bit more audacious. I will do something that is not exactly satisfied immediately for the minimal surface equation, but actually you can reduce to a setting where you can reason with that assumption. So I'm assuming there's a capital lambda so that this matrix is, and it's supposed to be at every point, is controlled like that, which obviously it's a symmetric matrix by Schwarz lemma. So I really mean that I compare it to multiples of identity. So for the examples we had, well, obviously for the Dirichlet energy, there's no problem. The second derivative of L is just the identity. And for the minimal surface equation, it's a little bit more annoying. So you'd get that the second derivative of L at P is identity plus P square, and then an annoying term, which is actually just the projection on P orthogonal, times 1 plus P square 3/2. Okay. It is certainly bounded above, because the denominator dominates the numerator. Bounded below is only true if you restrict to a certain bounded domain in P. But it turns out that for the minimal surface problem, you can reduce to that. Okay, so I exaggerate here a little bit by asking that it's true everywhere. But in fact, since we do everything locally, that's fine. You can always assume that where you want to study the problem, provided, sorry, I said locally in X. Sorry, I said something that was confusing. Here, this is P. It's not local in X. P is meant to be grad U, but it turns out that for the minimal surface equation, the grad U, we can bound it. Okay, so now the solution to the problem. Do I have anything to erase? Oh, I forgot to say in the beginning that what I present is the result of many different groups. I participated some paper. François here participated some papers as well. But I mean, it's the product of at least 10 or 15 or 20 people. It's not only the result of one paper. So back to the Hilbert 19th problem. And the solution, especially the last steps, have really led to a small revolution in PD analysis. So the first thing is Bernstein, 1904, which essentially tells you that if you have C infinity, you have analyticity. It's not so surprising. If all the derivatives exist, you have to check the summation of the entire series that it converges. It's a non-zero radius of convergence, and you fight brute force with the PD. Okay, then the second step, much more important, is the fundamental estimates of Hölder in the 30s. And Hölder tells you that if your matrix A is Hölder, so it's a local result, as always. And don't forget my matrix A is here, and it's here as well. Then Hölder looks at the non-divergence form. So then the equation 2 star, or the solution, sorry, to the solution U to 2 star, which, let's rewrite it, it's A dot dot. Okay, so by the way, this notation just means Aij D2ij U, where the repeated indices are summed, okay? It just means this. So the Hölder theory tells you that if you're solving this problem and you know the coefficients are C alpha, then the solution U is C2 plus alpha. Okay, we'll define some space. I'll write down some definitions in a bit when I start doing proofs, actually, but it's what you would expect it to be. It's having being C2, and the second order derivatives having some C alpha Hölder regularity. So you have the gain of two derivatives you would expect from this elliptic operator in the scale of Hölder spaces. At that point, you look at what is missing. Actually, very little, but it's where all the difficulty lies. So, in order for A to be Hölder, what do you need? That is a smooth function. So, by composition, if you would know that grad U was Hölder, you would know that then you would know that A is Hölder. So A is C alpha if grad U is C alpha. Now, when you look at the equation 3 star, one thing that was already known at the time, so I wrote it little f, but don't forget it's just one of the components of grad U. So on the equation 3 star, each decay U, which is actually what we call f, satisfies a divergence-free, divergence form elliptic PDE. U itself satisfies a non-divergence form. Using these two equations, you can have some maximum principal argument in order to find bounds on grad U, provided you do what you need to do at the boundary and everything. So the gap is here. People knew how to get pointwise bounds on grad U, and they needed to get some Hölder regularity. And if you wonder, yes, you could do something weaker than Hölder. Dini conditions can work. Actually, some good control on the modulus of continuity. But that's precisely what is not given by the previous arguments. So this is where comes the contribution of Nash and of De Giorgi and Nash. Before, just one decade and a half before they published, De Giorgi published, Moser gave a special solution in 2D, in the 2D case. So the solution arrived with the two papers written completely independently. So Nash in 57, no, the opposite, sorry, De Giorgi in 57 and Nash in 58. So De Giorgi was looking at the elliptic problem. Nash at the time was looking at the parabolic problem. So they are formulated a bit differently. The methods are completely different. You can see that they have not communicated at all. But in fact, both approaches work for both cases. So they are both valuable. So in some sense, the De Giorgi method is probably the most popular for geometric flows and in geometric PDEs. But the Nash method has really also had a huge influence, in particular for pointwise estimate on fundamental solutions. Many that also were used in the end by Yao and others in geometry. But well, they were both very influential, this proof. With the advantage that the De Giorgi proof is much shorter and much easier to read. But Nash proof was digested very quickly as well. Okay, so what De Giorgi proved is he considered, so I'm rewriting my equation 3 star. So he considered this equation and you take a matrix to be an a priori given matrix of coefficients that is measurable and that satisfies these bounds almost everywhere. So we have a matrix that is bounded, symmetric, sorry. It's a symmetric matrix. So you can see that A is meant exactly to be the second order derivative of L, taken at grad U. And he proved that if F is a weak, let's give a rigorous statement, F is a weak L2 solution, then locally, then F is locally Hölder for some alpha. And Nash had a similar statement in the parabolic case. Similar for dtf is equal divergence A grad F. So you see that it solves the problem because you will apply that to F being one of the derivatives of U and you bridge this gap. So in the end, you get the whole vector of derivatives of U being Hölder, and then you can start the Schauder estimates. Once you have gain C2 plus alpha, you feed that information back into your coefficients, and then you realize that your coefficients are not just C alpha, they are actually themselves C1 plus alpha, right? You lose 1 by the gradient. And then you continue. You can bootstrap, you can differentiate the equation. Obviously, I didn't say it, but the Schauder theory survives lower order terms nicely. It was actually written with lower order terms initially. So you just differentiate the equation and you redo the same on the derivatives of U. And you continue and you get to infinity and so on. Okay, so then the other contribution to this problem is, so in the early 60s, Jürgen Moser obtained a slightly different proof, well, no, quite different proof. I said slightly because the so-called first lemma of the Giorgi is very similar in Moser. The second is completely different in Moser. He obtained a different proof that also gives the Harnack inequality. So Harnack inequality is an inequality for an elliptic equation that relates locally the sup to the inf, the inequality that is the non-trivial one. Okay, you want to relate locally the sup to the inf by a universal constant that is only related to the rigidity of the PDE. Of course, the Harnack is a mathematician of the 19th century. It was known for linear PDEs with nice smooth coefficients. But what was new was to prove it with these measurable coefficients. Okay, the proof of Moser, well, it's interesting for PDE analysis because it starts with energy estimates. It looks more like PDE analysis than the Giorgi. In the end, there was a small gap in the very first paper that he filled in the second paper using a quite deep theorem about oscillating functions. And all of that, before he filled it, at the same time, Kruskov was reading both Moser and Nash, and at the same time proposed an interesting other viewpoint on the Moser-Nash, the Nash-Moser proof. Well, let's call it a simplification. I think I will have time to give you the main argument of Kruskov. This is in my, at least in the elliptic case. Something I want to say, maybe as a teaser, is that in Nash, Moser, and Kruskov, there's a fundamental role played by looking at the equation on the log of the solution. It's fundamental, and it really goes back to Nash, as far as I understand. It's a beautiful idea in his paper. It's inspired a bit by the entropy functional integral of f log f. In De Giorgi, you don't see it appearing at all at first look. But in fact, I'll try to explain why, even in the De Giorgi proof, there is some log hidden, in fact, in the estimates. Okay, so just a point of terminology. So the last steps are usually referred to as the Giorgi-Nash-Moser theory, sometimes the Giorgi-Nash. Well, of course, don't confuse it with the Nash-Moser theory, which is this form of implicit function with loss of derivatives, which was initially used by Nash for the isometric embedding, was extended by Moser. This is something different. There's vaguely a resemblance at one part of the proof, but this is something completely different. So the restrictions of this theory, the first one is, which one do I do first? Yeah, the first one is that the theorem of De Giorgi and Nash deal with divergence form equations. Same with Moser, same with Kruskov. And so you see what I mean, divergence form, the last derivative is out of the coefficients. And it's not at all a technical issue. It is absolutely fundamental because all the methods rely at some point on energy estimates. So for those of you not PD analysts, what I mean by that, energy estimate, it just means I want to be able to obtain an estimate on an L2 norm, for instance, by integrating. So if I integrate the PDE against, let me put it this way, if I integrate the PDE against typically a localization function phi square u, I want to be able to obtain some control on the grad u. And you see that here the divergence form is fundamental. It's a sort of symmetry structure. All the methods use that in one way or another, whether they call it energy estimate or not. So that restriction was studied a lot in the Russian school by many people, including Landis, for instance, and it was solved in a paper by Krylov and Safonov. It's also related to works of Alexandrov, I should say, Pucci and others. But I mean, the paper usually credited for giving the final answer is Krylov-Safonov, which should be 81, which gives, by a totally different method, the Hölder regularity when the coefficients are outside the derivatives, okay, for non-divergence. I wanted to mention that. I won't have time at all to deal with that for two reasons. In the case of non-local operators, the non-local operators can sort of be tweaked, rewritten if you want, to be looking both as a divergence form operator or non-divergence. So these methods have somehow also influenced the recent renewal of De Giorgi style work for non-local kinetic equations, but also because in full rigor, we don't have an answer about whether there is an hypoelliptic version of the Krylov-Safonov theory that I'll explain a bit later. We don't even know if it's true. So that is the first restriction. The second one is the second restriction is the ellipticity itself. So if you want to look at more degenerate Sometimes it was called ultra, sometimes it was called hypo, elliptic or parabolic equations. You naturally wonder whether the theory carries on. So typically, you want to look at, for instance, something like that. That's the first thing you might want to look at. So we are back to the divergence form. We have a certain number of, what did I call little n? N was my dimension. It doesn't need to be the dimension. Let's say up to R. Here we have vector fields, smooth vector fields, let's say. And your matrix here has the same assumption as what the Giorgi and Nash assumed. Okay? So A is measurable, symmetric, and has the control as always. Okay, then here now you want to know whether the theory carries on when the DI, the Lie algebra of your vector fields, meaning what you can construct with the Lie bracket being the commutator. So it's a standard Lie algebra, but the Lie bracket is what we usually mean by the Lie bracket in that context, is the commutators between your vector fields. Okay, and if your Lie algebra has full rank, so I forgot what I think it was a little n, the dimension of my space. If your Lie algebra has full rank everywhere, then the theory was extended. The theory extends. I don't want to spend too much time on that because it's neither very difficult nor very interesting. The standard estimates are actually rather straightforwardly extended. So that's I'll come back to that in a second. That will be the first way you can be hypoelliptic. And the second way is the motivation for these lectures. So this class of equations can be useful, for instance, in sub-Riemannian geometry. So operators writing like sum of second order terms where you have good commutator conditions on the vector fields. But the type 2 is the one that appears a lot in mathematical physics, is something that would look like, well, you'd have some first order, let me write it as T. First order operator here, plus the sum I wrote before. Okay, so this is where you want to extend the theory. That was open until until about 2010. The first results are Wang-Zhang and Pascucci-Polidoro. Which one is before? No, Pascucci-Polidoro is before, sorry. Pascucci-Polidoro is mid-2000, Wang-Zhang must be 2010. Pascucci-Polidoro is the first lemma of the Giorgi. Wang-Zhang follows somehow the Kruskov approach to get Hölder. And together with François, Alexis-Vasseur, and Cyril Imbert, we obtained, let's say, the full de Giorgi package with Harnack on top. It was non-constructive, but that was the complete theory that time. For a subclass, not the full generality. Okay, so now this is what motivates these works. Let me explain a bit more Hermander's theory of hypoellipticity. The second main motivation. So it is ubiquitous. Why? So it's very easy to see why. Actually, in the main paper, there are of course a forerunner paper. Every time I talk about that with Claude Bardos, he reminds me the paper. So this time I had written down. Where did I put that? I lost it again. Anyway, there were papers by Nierenberg and others in the 50s. But the first complete theorization of hypoellipticity is in this famous paper by Hermander in '67, where the starting point is a note by Kolmogorov in 1934. So let me explain for 5 minutes what is this. It's the motivation is very easy to understand. It's a beautiful question. If we try to understand the following property. So the property would be, let's say that if Pu is C infinity locally, then U is C infinity locally for an operator P. Okay? Another way to formulate it is if you have a fundamental solution, you want the fundamental solution to be C infinity outside of the point of the Dirac which generates the fundamental solution. That would be what Hermander called hypoelliptic. He doesn't want to call it elliptic because you don't have to be elliptic to satisfy that, right? So if you like the viewpoint of pseudo-differential operators, you want to say that there's no singular set, there's no way for the solution to oscillate, there's no hyperbolicity where you could propagate singularities. And if you want to think in terms of fundamental solution, you can have regularity directly read on the fundamental solution. So obviously, if you have a second order operator, I wrote some example. Yeah, well, that one is trivial. If P is a second order operator plus lower order terms, d(aij), d2ij plus lower order terms, and if your matrix A is smooth and elliptic, then you will satisfy that. But that's what we call an elliptic operator, right? The higher order term, the one that dominates, has ellipticity and so on. And the starting point of the paper of Hermander is to say, well, this is not, this is sufficient, but it's not necessary, even for second order operator. And the examples he gives is the example of Kolmogorov 1934. So I will write it as a PDE analysis, and then I will give the stochastic interpretation, which is more or less trivial. So I'm writing the Kolmogorov equation in its simplest form. It deals with a much broader class in the short note. So you have f depend on time, a position x, and a kinetic variable v, and you want to solve that with, for instance, some initial condition at t0, and then you can interpret f as the law of the following stochastic trajectories. Maybe there's a 1/2. I'm really not expert in it. There might be a 1/2 here, right? Yes, okay. But anyway, the key point is the title of the paper of Kolmogorov is something like time-integrated Brownian motion in German. You can see that it's really saying that, in fact, the second derivative of the position is doing the increment of the Brownian motion. So that's why he called it time-integrated Brownian motion. From a mechanic viewpoint, you see that it's like imposing, the noise is imposed as a force at the level of the force in classical mechanics. So you have some sort of inertia principle. So that's why it's so natural, right? You want to impose things only at the level of the acceleration, not speed. And Kolmogorov for that equation gives the following fundamental solution. Again, I specialize this formula to the very simple case that I wrote. So he obtains, so you take F0 to be, so I want to understand the fundamental solution. So you just take F0 to be a Dirac in X naught V naught, and you get the fundamental solution of that form, where I don't guarantee all the constants, but what matters really is the scalings. The last term is T V minus V naught over 2. Ooh, and also, I think I wrote it without the 1/2, so be careful. Right, you see what I mean? I think my formula doesn't have the 1/2 on the Laplacian. Anyway, it would just change the constants over T3 minus V naught squared over 4T. So you see, there's a part that looks like the fundamental solution of the diffusion in V somehow, with however a different scaling here. And this part is a complicated mixture of, well, it partly looks like the fundamental solution in X, except that you have operated a sort of Galilean translation well, a sort of translation. The 1/2 is not exactly the Galilean translation. And on top of that, the power here is not what you would expect. The ratio of power, 1 to 2, is not the same in both cases. So you have this fundamental solution, and it is smooth. You can see that it is smooth for T strict positive. So, so that is the starting point. And the idea is that the regularity, or the regularization, I should say, is transferred from V to X by the first order operator, which is this dt plus V grad X. And if you want to think about that in terms of the stochastic trajectories, you could say that the noise is transferred from V to X by this first order operator. So, so very simple image of that is, then maybe I'll do a few minutes break. A very simple image of that fact. Well, maybe I'll give the two images and stop. If you'd look at, so where did I put my axis? Yes, okay. Let's say each of them is in 1D, okay? X and little x and little v are both in 1D. And I look at, I adopt the stochastic viewpoint. I think about the stochastic trajectory. So in V, well, in V, you look at the equation, and I'm just solving the Brownian motion in V. So in V, I'm just doing a Brownian particle. Except that as soon as the velocity is not 0, I drift. The first equation tells me that I drift exactly by the speed given by this V. So if my Brownian particle starts moving to positive velocity, I start drifting, you see? And then I can drift faster and so on. Now, if you look at the shadow of this trajectory on the vertical axis, you would just see my original Brownian particle in V. But if you look at the shadow of that trajectory on the horizontal axis, you see a certain type of noise, which is not the same as Brownian. You see, well, the solution to the time-integrated Brownian motion, which is also noised. The second image that Hermander brought to the picture is much more geometric. So Hermander starts from the problem, this observation with this explicit solution by Kolmogorov, and then he looks at a general class of operators of that type. So I'm reusing the notation in the paper of Hermander. Sorry for the big X are not supposed to be coordinates. So all the X0, X1, XR are smooth vector fields. In the original problem of Hermander, there's no rough coefficients. And the idea of Hermander, the interpretation is that if the Lie algebra of all the vector fields has full rank, it means that by following, it means geometrically that if you follow, for instance, you'll have to think about what I'm drawing infinitesimally, but you follow a bit the first vector field, a bit the second vector field, a bit backward the first vector field, a bit backward the second vector field, you're not back at your starting point because they don't commute. I mean, if you assume that the Hermander condition, they don't all commute. Otherwise, you'd gain nothing in the Lie algebra. And what the vector field you obtain by this commutation property, if you have the Hermander condition, will create the missing direction that you didn't have in your diffusion operator. Okay, so that is the geometric picture of Hermander. And now let's write it. I'll stop on that for a little break. Let's write it for the super simple Kolmogorov operator. Well, so you can do it with dt to be exactly in the form of Hermander. X0 is that. I is dvi for I equal 1 to little n. And the total dimension is 2n plus 1, right? There is time, there is x, and there is v. Well, you now just observe that x0 commuting with xi. Look at what happens. That commutes with dt, so you don't see it. And then when you apply grad vi to this, there's one thing that doesn't commute when it hits the coefficient. And in the way I wrote it, I would get with a minus. You get minus dxi. So you get the derivatives in all x coordinates that were missing. And then by linear combination, if you have dt plus v dx, v grad x, you have all the grad x. By difference, you'll have dt as well. So here you have an archetypical example where you have the Hermander condition. So that's, yeah, let's do the break now. So first, a small remark following a silent look from François. When I mentioned Harnack inequality, I don't know if it's still on the blackboard. Yeah, for the Harnack inequality, you need also the little f to be non-negative. It needs to be valued in the half-line. Also, last comment on what I said last time, what I said before the break. When you have, where is it? Yes, this is, so if you look at my prototype equation, the one of Kolmogorov, the simple case here, you can see one thing that is actually interesting. Also, I won't do much about it, but I won't have time. If you look at this fundamental solution, you can see that, and you could also write it in Fourier. Actually, that's the proof of Kolmogorov, which, by the way, is not complicated. It's a two pages note in German in Annals of Math, the paper of Kolmogorov. To solve the equation, he combines a bit of Fourier transforming and Duhamel principle along the free flow trajectories. So that's just that. So you can also write down the fundamental solution in Fourier. And you have a sort of similar structure, and you see that the way it regularizes is similar to elliptic in the v variable, but very different on that one. And in particular, the exponent you see of fundamental, the ratio 3:1, and it encodes the number of commutators you need to recover all the directions. So in general, the sort of regularization you expect for an hypoelliptic equation with smooth coefficient and everything is, let's say with constant coefficient, would be of Gevrey type rather than analytic. Okay, so, and a related question that is interesting for us is what kind of bound you can expect, decay bound away from the diagonal you can expect for the on the fundamental solution more generally than that explicit solution. Okay, and by the way, it connects to the silent question of François, because the Harnack inequality, because of the work of Nash and Aronson and many others, is now largely considered as the first step towards estimate on the decay of the fundamental solution away from the diagonal, which is where you will also see showing up this difference of decay between elliptic and hypoelliptic. Okay, so now let me go to the third motivation, which is kinetic theory. So, well, let's say mathematical kinetic theory. So, if you're not from that area, where does it go in the history of mathematical physics? Well, obviously, the bedrock of that is Newton classical mechanics, and then you have lots of theories, electromagnetism, quantum mechanics, relativity, and so on. But what I'm particularly interested in here is what happens when you try to have a statistical viewpoint on classical mechanics, and this is for what we want to look at is really pioneered mathematically by Maxwell and Boltzmann. Of course, there are many other names in physics associated to this. One of the most mathematical as well is Gibbs, but you have many others here. But in terms of the mathematical theory we are going to talk about, it's Maxwell 1867 and subsequent papers, Boltzmann 1872, and subsequent papers, and the book as well that he wrote. So the key point is, I don't want to spend too much time on the physics, but here you have the trajectories of, let's say, mécanique du point, as we say in France. So you have the trajectories of 1, 2, 3 particles. Well, Newton famously solved the two-body problem. And then if the number of your particles become enormous, so typically in astrophysics, you have 10 to the 10 stars in the Milky Way. You have billions of galaxies. In chemistry, the Dro maybe, is 10 to the 20 molecules in a mole. And you have other models then for flux, crowds, and so on. So you have a very large number of individuals, and then you want to adopt a statistical viewpoint. So the picture after these papers and many others become like that. You have the microscopic world, this is the sort of beautiful world of Newton that we never have access to. You have the mesoscopic scale, which is the world of kinetic theory, where at a given point in space, you look at the distribution in this kinetic variable velocity of your agents, particles, stars, and everything, and you look at how it evolves in time. Here, your objects are the positions and velocities of each and every particles. And finally, you have the world of macroscopic fluid mechanics of Hölder, Navier, and Stokes. So that would be macroscopic. And so that starts even earlier, a century earlier, for the non-viscous case, and 19th century for viscosity. And here the object is, as you know, for instance, the fields. You have the density field, the velocity field of the fluid, the temperature field of the fluid. Okay, so the main motivation for what I will present is at that level. Even though there are some structures that are reminiscent of hypoelliptic hypocoercive at that level as well, but we'll look at this level. If you wonder why it's called kinetic theory, it's because of this variable. That's not very mysterious. It's because there was a huge controversy when this theory was proposed initially, because that variable is not accessible to observation. It's a hidden variable. So it shocked people. Whereas in contrast, when you write the Euler equation and Navier-Stokes equations, they are based on quantities in principle you can measure, whereas that you won't measure. So that's this kinetic variable gave the name to the theory. So what does it look like? The oldest equation in the theory is called the Boltzmann equation, but should be called actually the Maxwell-Boltzmann equation. I suppose Maxwell had already too many equations to his name, so he didn't fight for that one. But it's actually first written in the 1867 paper, and not in the Boltzmann paper. And there's never been any fight. I mean, Boltzmann starts by discussing the paper of Maxwell in his paper. I don't really know when the shift of name happened. So that equation writes like that: dtf plus v grad xf is equal to qff. And now, let me explain the equation, and then I will explain the transfer we are going to do from the de Giorgi-Moser theory to this field. So Q of ff is a nasty beast. So f is a function of time, position, and velocity, the kinetic variable. That is meant to be non-negative because it's meant to be a time-dependent probability density in position and velocity. And your operator is, okay, it's something, it's best I write it first and then I explain. So for the experts, I'm writing it with the omega representation, but we could choose other way. And then you have f prime. I think I'm going to use the whole blackboard because this is kind of annoying. I will not write it again, so don't panic. okay, so what is this? And then I'll write here the second most important equation in kinetic theory. So this is an equation devised by Maxwell for the statistical understanding of the collision process. So you have particles who travel happily in straight line, and then they encounter elastic shocks. For instance, it could be other type of shocks. I'll discuss that in a second. But visualize the elastic shocks. It's called the hard balls billiard. Then, what this operator tells you, the operator is just a balance sheet in velocity space of what happens because of the collisions. So every time there are two particles with velocity v prime star colliding to give two particles, one of which being with velocity v, then you count that positively. So that positive term is counting positively towards your total number of particles with velocity v. If a particle with velocity v collides elastically with a particle of velocity v star to give other velocities, you count it negatively. So this is just a balance sheet statistically of what happens in the velocity space. That collision kernel encodes the relative frequencies of the collisions. And to compute it, you have to solve a sort of scattering problem and see how frequent it is that particles collide with that or that difference of angles before and after collision. So there's a whole calculation to be made that is just the classical mechanics calculation on the elastic collision. So I didn't tell you how were my v prime star related to v star. Well, in that representation, that choice of parametrization I did, they are related like that. So that's your inner product. And they are related like that because you're solving the elastic collision. And in the elastic collision, you have conservation of mass. And here I'm assuming all my particles have the same mass. So the conservation of mass is trivial because it's just two particles giving two particles. You have the conservation of momentum, which is v plus v star is equal v prime plus v prime star. And you have the conservation of energy, v square plus v star square equals v prime square plus v prime star squared. And you can check that these conservations are faithfully inherited by the operator, meaning that this operator will not change the integral of f against 1, the integral of f against v, the integral of f against v square. So the picture, which I will need in a second to tell you about the lambda operator, looks like that. You can check that. So 0 is here. I'm just drawing the four velocities. You can check that these two equations mean that the four particles, the four velocities live on a circle of that form. Okay, it's very easy. That tells you that if you divide by 2, you see that the halves are the same, the centers are the same, and with the other one and a bit of Pythagoras, you will see that it forces that shape. Now, before I give you the kernels, I just want to motivate the problems I'm going to write by saying that this is a hard equation. Well, as of today. Maybe there's been an archive preprint this morning, But as of today, it's an equation that we don't know how to solve in full generality. So it's a difficult PDE. Well, some structural arguments. You can see that it is nonlinear. Well, it's actually bilinear. You can see that it's non-local. And it's non-local, annoyingly, it's non-local in a way that is hard, and in some sense it's not non-local enough that it would help you. But by that I mean that it's not non-local at all in X. If it was, actually the equation would be infinitely easier. You see what I mean? Because in position, what you have on the right hand side is almost like the square of the solution, which is very bad in terms of nonlinearity. It's non-local, but not enough if you want. The scalings are a mess. If you're used to Schrödinger or Navier-Stokes, you might be used to PDEs that behave very nicely with a certain number of scalings that allow you to determine critical spaces and everything. It's not the case for the Boltzmann equation as far as I know. So that's another difficulty of the problem. Now, another argument for how difficult this PDE is, if you define rho Tx being the integral in the kinetic variable of your probability density, you defined like that. So instead of dividing by rho, I write directly the momentum physically, being the integral of v times f v xv. And finally, rho t, or maybe let me call it theta to not confuse with time, being 1 over dimension integral in v of v minus u squared f t x v. So you just define these three things. They are called the hydrodynamical fields. I'll come back to them in a second. These are the things you really can observe in your gas. You know, in the molecules in the room, you don't really know at a given point what is the distribution of their velocities. What you could measure is a temperature or a local vector field, impulsion field of the gas, momentum, sorry. Then, in certain scaling limits that I really don't want to start writing now to save time, but if you're interested, I'm sure François will tell you everything about these scaling limits. In certain scaling limits, you can obtain compressible and you can obtain compressible fluid dynamics, meaning Hölder, with first order correction giving you the Navier-Stokes term in the compressible dynamics, and in a slightly different scaling limits for certain small perturbations of the equilibrium, you can even find the incompressible Navier-Stokes equations. So, so you can't expect really a miraculous Cauchy theorem on that equation. It has, in some sense, it's not a proof, but it has to contain all the difficulty of these other monsters. Okay, so that is a hard equation. And now let me go back to the question of the kernel. So the collision kernel, B, was calculated in two cases in the article of Maxwell, 1867. So B is equal to so this B actually takes the form of mod V star sine theta, where theta in my picture is just this. For hard spheres, sorry. HS stands for hard spheres. Okay, so the colliding billiards. And another case that was calculated by Maxwell, that is the one motivating the mathematical physics problem that motivates extending the Giorgi methods, is when we consider a repulsive force. So here I have a little b function, cos theta, where this little b function cos theta is equivalent for small angle to theta minus, I want to write it correctly, minus 1 minus 2s, minus 1 or minus 2? Yeah, minus 1. Minus 1 minus 2s with gamma is equal to alpha minus 5 over alpha minus 1. Yes, and s is equal to 1 over alpha minus 1. Yes, I put the 2 here. Okay, that's good. For so this first case is for hard sphere, and the second case is for repulsive force between particles that scales like r to the minus alpha. Okay, this is a cascade of formula, but no panic. It's easy to make sense of them. So there's a very helpful parallel here for this class of integral differential operators. Well, integral operators for Q and integral differential equation for the whole Boltzmann equation. For Q, this part of the collision kernel plays the role of the growth or decay of the decay of the coefficients for a standard differential operator. Okay, so if gamma equal to 0, you would compare that to a constant coefficient differential operator. If gamma is strict positive, you would compare that to coefficients growing at infinity. Okay, and in this parallel, the singularity at small theta of little b is comparable to the order of fractional derivative of your derivative part of your operator. Okay, so s equal 1 being the limit case where you have a diffusion, two derivatives, a second order derivative. S equals 0 being the limit case where there is no derivative. Actually, you have to interpret it correctly. If you plug formally s equals 0 here, you still have a log derivative. But I mean, okay, still, what I'm saying is morally correct. So, and if you wonder why do I still have my particles colliding, yes, there. If you wonder why we have a singularity, it is easier to think of it on the particles. So the Boltzmann-Grad limit is a certain limit where the way, so if you have two particles interacting, the Boltzmann-Grad limit will scale the whole interaction to a point anyway in the end. So the only way in which the type of interaction you had initially is captured by the equation is in the kernel. That's the first observation. That's the only thing that remains after the Boltzmann-Grad limit from the type of interaction you had. If your particles have to collide by contact, okay, and then, you know, they leave, it turns out that if you choose properly the parametrization, well, it's not exact. You have to parameterize by another unit vector than the omega, but it doesn't matter. It turns out that the statistic distribution of potential deviation is uniform. That's the hard sphere case. Because when you have to be in contact to hit and deviate, it's not more likely you will have a strong deviation or a small deviation. On the opposite, when the particles interact at a long distance, it's a question of the how do we say in English, the visible angle at which you see the other particle, it will be the longer the distance, the more likely it is that in most cases, the particle will influence each other only very slightly. Okay, so that is the reason for the singularity. When the interaction is at very long distance, there are much more cases statistically where they start interacting at very long distance and their deviation angle is very small. So this is seen here. All of that to say, I hope I convince you it is not a technical problem at all. Not at all. It's really dealing with the singularities in this little b is really dealing with the long distance interactions of the real dynamics. So here is a problem. Problem 1 of mathematical physics. Well, the full problem would be existence of global smooth solution to the Boltzmann equation and asymptotic behavior. But okay, we are very far from that. Problem 1 may be more doable, and part of it now is solved. Problem 1 is if the fluid part, so if the hydrofields are controlled pointwise, meaning everywhere, you assume bound from above and below as suitable as you need. Can we and we look at long range case. So the long range case is when we have the little b singular. Is it true that the equation is regularizing? Is the solution instantly smooth? I don't want to write more avalanche of formulas, so that's why I keep it formulated. So this is the so-called conditional regularity. There was a related previous conjecture of conditional relaxation with a sort of similar assumption. You could ask whether an a priori solution would converge towards the thermodynamical equilibrium, which was solved by the joint effort of Carlen, Carvalho, Laurent, Devillet, and Cédric Villani. And I participated in that conditional relaxation for the last step to obtain the exponential decay. The conditional regularity, after lots of efforts, is known. So there are many papers, but the most definitive one which actually, well, I should say, the first steps in this program is Luis-Silvestre. The second main step is a series of papers, a very nice paper by Cyril and Luis, who obtained a positive answer to this when your alpha is greater than 3, right? I'm trying to remember. Yes. For alpha, so for long distance, but not too long distance. So that's called moderately soft potential in the jargon of kinetic theory. And that uses heavily all of the stuff I'm going to talk about. It is based on a lot of theory, a la de Giorgi, a la Krylov sometimes as well. Okay. You could imagine variants of that problem. In the Hartshield's case, the best way you could imagine a meaningful question is you can't have regularization per se in the hard sphere case, but you could ask whether if the hydrofields are controlled, can you propagate the regularity? There is a problem too, and I have no idea whether it's related to the regularity theory, but it's more conditional because It's related to the recent preprint still being checked. So there's a recent work by Deng, Annie Wang on the Boltzmann grad limit, so which is how to go from that step to that step. But as far as I understand, which is certainly not the whole paper, I don't understand the whole paper, but it does not apply to long-range interaction. So is there a way to have an extension of that paper to long-range interactions for these singular kernels? Okay, that I'm just mentioning it because it seems to me possible that it would require a good amount of regularity theory with some of these methods. Now, because in this course I'm not sure I will have time to really deal with non-local operators, I want to present the second main motivation, which is the way I started working on that with François, Cyril, and Alexis, which is the limit case alpha equals 2, which is the Coulomb repulsive interaction. So in that case, if you accept my hand-waving parallel, so what happens? Okay, that gamma becomes -3, so be it. Okay, it's very singular, but the main problem is that this singularity little b wants to become an order of differentiation that is the Laplacian. And the operator becomes ill-posed. The Boltzmann operator makes no sense anymore for alpha equals 2. It's annoying because this is the case you want to consider for plasmas. Even though plasmas have a low level of collisions, they still do play a role. And if you want to understand the collisions between electrons in the plasma, you want absolutely to consider this case. And so Landau proposed in 1936, 6 I think. He proposed a modification of the Boltzmann operator that has this form. So you write the same equation. So I write it as Landau-Coulomb, but I think it was a fashion in the community to call Landau-Coulomb because people could only work on Landau, not Coulomb. They made some less complicated version of the operator, but let's just call it the Landau operator now. And this operator is still quite nasty, but it's already an improvement over the previous operator. And you will see where it's going to. So I know it still looks bad, but it's much better. Okay, so, oh, and I forgot my kernel, obviously. Sorry, should I put it here? So that V star is in RD, and here I have V minus V star minus 1. Okay, so what does it mean? Yeah, we still have the two operators. So that's not the way Landau wrote it. And there is a constant which I dropped, which Landau actually calculates. You can find it in the original paper on Landau or in the Landau-Lefschetz textbooks, one volume, I forgot which one. I think it's in Kinetic theory volume. But so what happens is that Landau writes it by some sort of conservation arguments, but in a more modern way, it was reobtained by the so-called grazing collision limit. If you look at this operator, and you scale properly the collision kernel capital B here to concentrate only on the theta equals 0 angles, with the right scaling, you will obtain that operator. So that projection, you project on V minus V star orthogonal. If you look at that and that picture, it should be very simple to understand why. You see, if you get that this angle goes to 0, look at what happens. The V star, in the end, infinitesimally, will have to be in the orthogonal tangent space to V minus V star. This is where the projection comes from. That's all. That's just this. And knowing that, if you look at that in the eyes and you Taylor expand, you will arrive at that operator. Then, of course, to justify, you need to work with estimates. But it's just this. So now, this operator has really the structure of it really can be written like that as a drift diffusion operator of that form. So this is what motivated us in the French kinetic community. The Italian group didn't start from that motivation. It was much more internal to ultra-parabolic equations and hypoelliptic equation, and neither Wang-Zhang. I think Wang-Zhang, it was also more internal to hypoelliptic problems. But so for this class of equation, you want to mimic, and maybe that's a good time to say what I mean by that. Well, the key idea we want to use from the Giorgi Nash Moser is, well, many ideas, but the first idea we want to use is to trade nonlinearity for linearity with low regularity coefficients. That is really the starting point of their approach, and that has been extremely influential. So you see that that matrix of coefficients A actually depends on F. You see what it is, in fact, secretly. It's just this sort of weird convolution-like term. You see, you take this whole integral here, and that creates your matrix A. Then you have divergence and you have grad, and you find this. So of course it depends on the solution. Same with the B term. Okay? So when I say you trade, you will say, okay, let's ignore it depends on F, and let's try first to understand that linear equation with rough coefficients. And then try to bring it back, to go back then to the nonlinear problem, and to try some bootstraps. So this is what we mean by exporting the Giorgi Nash Moser theory. We somehow forget the whole variational problem of Hilbert, which, by the way, is, I'm not happy with that. If there was any way to interpret, even in a larger space or whatever, this equation as a variational problem, that would help us a lot. So if you have any idea on that, that would be great. But so far, we don't know that. So we only use the last steps of the whole 19th problem of Hilbert, and we try to obtain this equivalent step that were first proved by De Giorgi and Nash. So problem 3, well, would be, so there will be, of course, the existence, uniqueness of global smooth solutions. So here it is a smooth solution to that equation now. Let's call it lambda equation. So this is, I think, also a bit out of reach. However, I want to report here So it is very hard. Same remark applies than here. You have the same scaling limits, so it should be a very hard problem. But it is worth mentioning a beautiful, absolutely beautiful, rather short paper by Nestor Guillen and Luis Silvestre in 23 or 4, maybe early 4, who have actually solved the question of global smooth solutions, but without x variable. You consider f that only depends on t and v, which is of course a significant simplification of the equation because you don't have fluid mechanics anymore. But it's still, the equation is still very far from trivial. So they obtained a new Lyapunov functional for this equation, which actually happens to be just the Fisher information in the end. But anyway, so problem 3, same thing. Can we have conditional regularity for the equation L in the same way as for Boltzmann equation? The meaning is exactly the same as before. Okay, so it's still written somewhere. It means you assume that your hydrofields are bounded, that you control the rho, the u, the theta at every point. In fact, bounded from above, and for rho you also want a bound from below to avoid vacuum. And then you ask whether you can prove, starting from a non-smooth data, that it's immediately smooth. When I say conditional, it means, I don't know if I was very clear enough in the first time. When I say conditional, it's a huge assumption. I will assume that these hydrofields are bounded for all x and also all time in the time interval I'm looking at. So I'm assuming something no one knows how to prove for the moment. Okay, so it's a big assumption. But still, this sort of theorem really, I think, is meaningful in mathematical physics because it means that if any singularity occurs, it has to occur at a fluid level. Or in other words, it has to occur in a way that is observable. Because if it was occurring on the kinetic variable in a way we can't detect, we can't measure in fluid mechanics, that maybe I think would be a bit worrying. Anyway, that problem is partially solved as well. It's solved for a modified version of the lambda equation where you change this power. So if instead of -1 I put gamma plus 2, it's a complete artificial modification of the equation. The gamma is just here as a parallel to the Boltzmann kernel. So you see when gamma is -3, I recovered the exact lambda operator. And now it is known how to do this for gamma greater than -2, I think, yeah, strict. So I think my time is almost up, so maybe I can just comment on these things. And yeah. So, by the way, the partial answers, I say partial, but they are nevertheless very interesting. Both partial answers are the combination of many papers. So the first, I presented first Boltzmann and Landau, but historically, the first one that was looked at was Landau. So, for instance, to take that question, the first step, in some sense, but not motivated by the Landau equation at all, was Pascucci and Polidoro in 2004. They obtained, let's say, the first half or first 30% of the Giorgi argument. Then Wang and Zhang managed in 2010 to obtain a version of the Kruskov argument for a modified equation that includes that class. a sort of equation they cook, but that includes that class. And later, when was that published? 16 or 17, I never know. In the paper with François, Cyril, and Alexis, we covered explicitly that class and discussed the link with the lambda equation. We added one thing. We didn't only use the hydrofields. We used also that the whole F is L infinity. And that is due to the problem of controlling the zero order term. And then there are works by Silvestre to get rid of that part, but only for, so you remove F L infinity, but only for certain gammas. Strict, I think. And bootstrapping to higher regularity, we only did Hölder and Harnack. Bootstrapping to higher regularity was done actually by me and Cyril, but also by Anderson, Snelson, by other techniques. So it's actually extending the Schauder estimates. So that just gives you an idea. For Boltzmann, it starts with Silvestre for the L infinity bound. Then there is Imbert-Silvestre for Schauder and Harnack. And I participated on the side the decay moment estimates with Cyril and Luis. And my recent PhD student Amélie made their theorem constructive, which it was not initially. So just to say that there's a lot of different papers for each. And even though it's partial, yeah, it required a lot of work. So in both these questions, I emphasize that the gap, what is missing, is morally the same. It's going to the very long range. It's going to the true singular behavior. Okay, so I continue on Friday, yeah.
Question avant le thé.
Yeah. Thanks for the question. So at the beginning you mentioned the Krylov-Safonov theorem. So what is the situation for the hypoelliptic situation? Is it expected to be true or?
So good question, because we've been looking at it a bit more in detail with Amélie, precisely. So here is the situation, as far as I know. I mean, if I've not missed papers. So in the elliptic case, so let's say you have that in the elliptic case. Let's call it U, whatever. What was known is Schauder, okay, and then you have sort of slightly more general version of Schauder. Then a big step was Cordes, probably in the 50s. And the Cordes argument was rewritten in a way I understand way better in the beautiful book by Landis, originally I think in Russian, but there's an English edition by the AMS. So I didn't know this book, it's absolutely beautiful. This book is published in the 70s. So that was before Krylov-Safonov. You will see why I mention it here. So they tell you that if they have a condition on this matrix A, which is, I mean, the meaning is obvious, I just want to write technically the good one. You say that if the trace of A divided by the smallest eigenvalue and you say that this is less than n, the dimension plus 2, and I think it's strict, but I wouldn't bet my life on it. But anyway, so you see, it tells you it's a very rigid condition. It tells you that the matrix is not far from being diagonal with the same eigenvalue on all entries. Then you have again the Hölder regularity. Okay, so that was what was known before, and then you had the wave of Alexandrov, Pucci. Like the Alexandrov,
yeah.
So that I know how to extend to the kinetic case.
Or the coordinates.
Yeah, and
you know how to extend.
but I mean, it's a bit long to write technically, but it's not so surprising. I mean, there's nothing really monsterly challenging. But we also realized that there's a group of Italians who were just doing that recently. So it is published, or it will be published. It's good to know, but that extends. The condition changes. Interestingly, the exponent is different in the kinetic case. Now, the big step forward is the ABP. Yes, the ABP estimate, which is the improved maximum principle. Either you see it as the original maximum principle of Alexandrov. So the maximum principle of Alexandrov, in some sense, if you're not familiar, my way of understanding it, you improve the way you depend on the source term by reducing the Lebesgue exponent on the source term. And it's highly non-trivial. I mean, it's really hard to prove. And in the form ABP, it looks a bit different, but it's actually equivalent. That we don't know how to extend to the kinetic case. So you would like to extend it to something of that form.
Well, I suppose with the A outside, no?
Oh, sorry, of course, sorry, the A outside, yeah. Of course, sorry. Yeah, the A like that. I wrote it for elliptic, but all of that works for parabolic as well. Sure. So for me, this is really that would be the interesting question. It could fail as well. I mean, I'm not totally sure it has to be true. Louis, for instance, was quite pessimistic, but I mean, if it fails, finding a counterexample would be interesting as well.
D'autres questions? Alors, so we can see the situation here. So what you think in the next 5 years, kind of reasonable goal will be, especially in the alpha constraint? You think it's not reasonable?
No, I suspect there's something. I hope. What I really would hope that this major progress, it's a new Lyapunov function that actually holds in the deep ocean, the deep ocean for the very singular case.
Even for the...
Yes, it was actually designed directly for the most singular case. Okay. It was extended to Boltzmann in the most singular case by Cédric, Cyril, Louis, and Nestor. Of course, it's homogeneous, but morally, my hope is that these new functionals should be able to, hopefully, to replace. Yeah, because the step we miss to go to very singular is really the first one. It's having the very first control to start. Yes, the very first one.
Say it again, I missed this point.
So, it's speculative, François. Yes. Remember. So, because Frank asked me where it could go, my hope is that the new functional, the new decay of Fischer by Guerand-Silvestre, could be, of course, it's spatially homogeneous, but nevertheless, it's the first real new estimates we have in the very singular case, could help to start the program, because in the conditional regularity program, this is only the first step that we miss in the very singular case.
What do you mean by the first step is the...
FL infinity.
Oh, yeah, you mean the result of, I mean the first lemma or whatever.
Yeah, because afterwards, L infinity to Hölder, we have them both for Boltzmann and Landau, even very singular.
Yes.
So...
Wow, so that's the key point.
I would love to see some interaction between these two things. On that regularity program. And the other thing I think that will develop a lot, I've not had news from you, Jay, maybe you had, maybe he has continued on that, is the boundary regularity. There's a lot to do, it's just starting for this class of equations.
Okay, good. Thank you again.